Hey everyone, today we're gonna be going over just the old basics of quadratics because I didn't have anything else to do. So, first, before we go into the general form of a quadratic, which is ax squared plus bx plus c, let's talk about polynomials as a whole. What is a polynomial? Well, it's made up of two parts. We have poly and nomial, so let's talk about what poly means. Poly in math, you can think of like polygons, or just, well, polygons are shapes with more than one side, so they're not straight lines, or, well, a circle is infinite. So the point is, poly generally just means multiple, and nomials is like a number, so combined it's like multiple numbers. More specifically, it's multiple algebraic terms that are typically raised to some power. Well, yeah, they're raised to a power, and it's the sum or difference of them. Could be plus or minus, doesn't really matter, still a polynomial. If this were ax squared minus bx minus c, it's still a polynomial. However, if it were ax squared over bx, like a fraction, it's not a polynomial because that's not a sum. It's fractions are dividing, so it's not a sum. So that's not a polynomial. But the basic idea is any equation where it looks kind of like this, or even like some of your like linear equations or whatever, those can be considered polynomials, so long as, you know, they're not. It's not like a rational function, which is a function where your x term is like being divided, so like 1 over x or whatever. Essentially, rationals are like fractions where they have different restrictions than these. So now that we have a pretty okay understanding of polynomials being just the sum of multiple algebraic terms, where those terms are being raised to a power, in this case it's being raised to the second power, let's talk about the fundamental theorem of algebra. So what is that? Well, in order to discuss the fundamental theorem of algebra, let's actually look at a quadratic. So we have y equals x squared, just a parabola. Now, this is different from most graphs you've been working with since, you know, you started basically at any point in time before you started learning about these. Your graphs were likely just like straight lines, like y equals x, like just a straight line. Or if they weren't straight lines, for instance, sine of x, if they weren't, you were likely just evaluating whether or not it was a function, not what the function actually is. So anyway, enough of that. Let's talk about the fundamental. This is a bad example. There you go. Okay. Let's talk about the fundamental theorem of algebra and what it states. Fundamental theorem of algebra essentially states that for a polynomial of nth degree, where the degree is just the exponent, so in this case this would be a second degree polynomial. If it were a cubic, meaning being raised to the third power, be a third degree polynomial, essentially states that for an nth degree polynomial there are exactly n number of roots, where roots are just when your function touches the x-axis. So most of you might know this as the x-intercept, or when y is equal to 0. So on this graph, we have two spots where y is equal to 0, 1 and -1. These are our two x-intercepts, if you will. I'll be calling them roots from now on. These are our two roots, or the zeros of our function. And let's talk about why we have two in a more mathematical sense. Let's look at -1, right? When you square something, you're multiplying it by itself one more time. So -1 times -1, two negatives multiplied together gets you a positive, so you have 1 minus 1, that's 0. And of course, 1 squared is just 1, minus 1 is 0. So far, this seems to add up with our fundamental theorem of algebra. We have a second degree polynomial, and we have two roots to represent that. So now, let's talk about, there are a couple like cases where they won't touch. In fact, let's look at one of them. +1. Now it's like, oh well, for a for a fundamental theorem, it's kind of crazy that, you know, it's not true here. And this will, well, I'll talk about this a little bit later in the video, but this is a case where the roots are not real, not in the sense that they're fake roots, if you will, but that they're not real as in they don't exist in the real numbers, which maybe I'll make a separate video on just the classification of numbers. But for now, just know that they are not real solutions. So basically every number you've ever seen up until now is a real number, you know, whether it be 3, -1, or pi, it's a real number. But there are other classes of numbers, namely imaginary numbers, and this is what we call, or this function rather, has imaginary roots, but we won't talk about that. So now that we've seen the graph, I just want to make a table of values for people to understand why the graph looks the way it does. So for any, let's just use our -1 example, for instance, right? So let's make a bit of a table. So this is our x, this is our y. Let's go and plug in a couple values. So if we plug in 5, well, plugging into y equals, I should probably write that, y equals x squared minus 1. Plugging in 5, we get, well, 5 squared is 25, minus 1, 24. Now if we check that here, let's go to 5 here. And as we approach 5, yep, we get 24. However, if you notice, on the other side, as we approach -5, we also get 24. Why is that? Well, in the square function, or rather squaring something, squaring a real number will get you positive output. So we plug in, oops, -5, we also get 24, as shown by the graph here. So we can try again. Let's try 3. 3 squared is 9, minus 1 is 8. And namely, or similarly, plug in -3, you also get 8. So let's just verify that on the graph. As we approach -3, we also get a little, there you go, we also get 8. And on this side, as we approach 3, we also get 8. So as you can see, this kind of, there's this nice level of symmetry amongst the positive x-axis and the negative x-axis, where they essentially mirror each other because of the square term, or rather, because we're squaring the x term, no matter what it is. So that gives you a little bit of insight into why there's this level of symmetry when we look at the graph of this. Now, how do we actually, beyond simply, plugging in values, a lot of times you'll see you want to get some basic quadratic, and they set it equal to 0. What does that actually mean? Well, beyond just looking like a scary equation, we have to recognize that quadratics are in essence a function, meaning just like you've seen before, we can say y is equal to ax squared plus bx plus c. And when we set a quadratic equal to 0, we're essentially plugging in 0 into our y. We're asking, when y is equal to 0, what is ax squared plus bx plus c? And this is finding the roots, or finding the zeros of our functions. So let's talk about ways we can actually do that. So, most of you have probably heard quadratic formula. It looks a little scary, but I'll write it out. So x, in this case, because I guess I should have said this earlier, but a, it's a coefficient, meaning it's just multiplying whatever x is. Similarly, b is a coefficient, it's multiplying whatever x is here. C is easy to remember. C for constant, it's just a constant term. It's kind of like the y-intercept in linear equations, where if you had like y equals 3x plus 1, in this case 1 is a constant, it just shifts your graph up so that rather than starting at the origin, it starts 1 above the origin. So that's what the c term does here. So let's just add another x term here. Let's try 3x. So now we've shifted our function over a little bit. Let's try subtracting 3x. We also shifted over a similar amount, and if we just remove this term, it recenters itself. See? So now, let's look at the quadratic formula. So x is equal to negative b plus or minus the square root, I need that to be a little bigger, b squared minus 4ac, and this whole thing is divided by 2a. Now, upon your first inspection, this probably looks pretty scary. But, as the school system would have it, you're probably just going to learn that all you need to do is plug the numbers in for this, and bam, you get out an answer. Doesn't matter what that answer means, or how this was actually derived, just plug it in and get an answer. I don't really want to do that, so what does this actually imply? I'm not going to go over a proof for the quadratic formula, because I'm not smart enough to do that. I am also not going to go over the way you derive the quadratic formula, so I'm also not smart enough to do that. But I can tell you what the answers you get out of this actually mean. So let's think back to our original problem. We have some function, right? Y is equal to ax squared plus bx plus c. We have it equal to a quadratic. And when we set y equal to 0, we're asking, well, what are the x's when y is equal to 0? Or in other cases, at what spot on the x-axis will this be touching? It could be, 2, 3, 4, 5, whatever. It's just when it touches the x-axis, where does it touch the x-axis? That's what we're trying to find out. And that's what the answers to the quadratic formula actually mean. So let's go over... Let me move this. Oh. Let's move that far. Anyway. So let's go over... I should have planned this out better. I don't have a quadratic to solve. Let me find one. Give me a second. Let's see. Let's find an easy example that actually has real roots. Let's see. That is not a quadratic that I want to solve. Okay, here we go. So let's say we got a quadratic. It's just x squared minus 6x plus 5. How would we solve this using our quadratic formula? Going a little out of order because quadratic formula is infinitely more famous than factoring. But, we'll go over factoring after this. So how would we solve this? As a general rule, when you're first starting out to solve quadratics, you should always list out what your a, b, and c are until you get a little more proficient, so that's what I'm going to do here. Remember, when there is no coefficient of 1, it's actually, I guess I spoiled it. When there's no coefficient of x, it really is an invisible 1, because when you multiply something by 1, it doesn't change. So a, in this case, is equal to 1. B is negative 6. Remember, this number takes the sign of, the sign that's next to it. So b is not just 6, it's negative 6. And c is easy, it's just 5. There's nothing, no x next to it, it's just 5. So, and another general thing is, for instance, if this were to be rewritten as negative 6x plus x squared plus 5, it doesn't mean that our a is negative 6. A is always the coefficient of the x squared term, so you would actually have to rewrite it into the form I have it as here, so don't get mixed up. Now that we have our coefficients and constant term laid out, what do we do? Well, we can just flat out plug it in. So negative 6 into, my b and 6 look a little similar, but okay. So negative 6, since this is negative b, it would be negative 6, which is just 6, positive 6, plus or minus, and I'll get into what that means once we simplify this down a little bit. The square root of b squared is 36 minus 4ac. Well, a is 1 and c is 5. So 1 times 5 is 5, times 4 is 20. So we subtract 20, divide this by 2a. Once again, a is just 1, so divide by 2. Now, how can we actually simplify this down? Well, 36 here minus 20 is 16. So we get 6 plus or minus the square root of 16, which is just 4, and we divide that by 2. Now I'm going to talk about what plus or minus means. As the name implies, it is, well, I guess not plus or minus, it's plus and minus. That's why we have two answers. Like I said earlier, with the fundamental theorem of algebra, it touches the x-axis twice, so when you solve quadratics, you're actually going to get two answers, assuming both roots are real. In certain cases, it may have one real root, may have two, may have none, as you saw with the y equals x squared plus 1 example. But as a general rule, with most quadratics, you're going to be solving for two answers, and that's why we have the plus or minus, because it gets us two answers. So let's try the plus first. Just 6 plus 4 is equal to 10 over 2. So we get 5. And we would then have to do the subtraction term. So it would be 6 minus 4, which is 2. And then 2 over 2 is 1. Therefore, it's not x equals 5 or 1. It's x equals 5 and x equals 1. So now let's plug this into Desmos to see what it actually looks like. Yeah. So x squared plus, minus 6x plus 5. So here we have our parabola. That's the shape. I should have mentioned that earlier. That's what this shape is called. It's called a parabola. And if we look at our roots, we have 1. So we did get that one. We got x equals 1. And we got x equals 5. So we were right. This is when y equals 0. That would mean that x is equal to 5. X is equal to 1. So that's a pretty quick, easy example of solving a quadratic by using the quadratic formula. Now let's do one of factoring. I don't exactly want to erase all this because I painted the whole thing black. Oh well. Now I have to fill it back in. There we go. There we go. Okay. So I'm gonna leave the quadratic formula up, but let's do one where we can factor. Or I guess I should explain what factoring actually is. So when you think of multiplication, right, we have the product, which is the answer to a multiplication problem. So for instance, a times b. The result of a times b is ab, and that is the product of those two terms. But the terms that actually multiply together, those are called the factors. So as factoring implies, the name factoring implies, it implies that you are thinking of things that multiply up to make your original quadratic. So in this case, our quadratic is the product. We're looking for two terms that multiply up to make it, to make that quadratic. Hence the name factoring. Kind of like reverse distributive property. So like if I had like 3 times x plus 1, you would distribute the 3 into the x and the 1, so this is the same as 3x plus 3. But if I had 3x plus 3, I could factor out a 3 and reverse it into 3 times x plus 1. So this is a sort of an easy example, but you can always check whether or not your factoring is correctly simply by multiplying out the terms. Now, with quadratics, it gets a little trickier. I don't have to erase that. Because we have the x squared term, we know it's going to have to be more than 1x, right? So every quadratic, or not every, certain quadratics will have a coefficient in front of x, but for the ones I'm dealing with, you're always going to need two x's to get your x squared term. And then for the rest of the terms, we're looking for something that adds up to b, so the coefficient not bx, but just b, and multiplies to get c. The way I remember that order is you learn multiplication before you learn, you learn addition before you learn multiplication. So in the same way, you have to find two terms that add up to b and then multiply to c. So let's think of a quadratic. So we have x squared minus 4x and then plus 4. Right, you can always, you could probably already see where this is going. But like I said, you're always going to need two x's, right? So we're just going to flat out write two x's right off the bat. X and just x, because this will multiply to get us x squared. Now let's look at our b term, which is -4. What two numbers add to -4? And I should have said this earlier, but you don't restrict yourselves to just positive numbers. You can go negative numbers as well. Generally, we want integers though, so whole numbers. We don't want fractions. That kind of messes with things. So try to, when we factor, we try to go for whole numbers. So thinking of numbers that add up to 4, we know 2 plus 2 is 4. -2 plus -2 is also, well, not also, but it's -4. So we have that down. And similarly, we can also now see whether or not -2 and -2 multiply to get 4. So we have -2 times -2 does in fact equal 4, and -2 plus -2 gets us -4. So we found how to factor this. It just factors out into x minus 2 times x minus 2. And that's what we fill the missing spots with. The numbers that add up to b and multiply to c. And of course, like I said, we could check our factoring, so let's multiply it out. X times x is x squared, as I said. X times minus 2 is minus 2x. Then we do that again. -2 times x is another minus 2x. And I'll write this down here. We can combine these terms, which gets us -4x. So that's our next one, minus 4x. And then we multiply -2 times -2, and that gets us positive 4. So our factoring was correct. And now, not every example is going to be this easy. Not every example is going to have the ability to be factored. Depending on what you're doing, some equations may require you to do what's called completing the square, which I'm not gonna do here because that's not something I'm very good at. But essentially, there's different steps for completing the square, but the general thing is if you have a coefficient for x squared that's not 1, for instance, if we had 3x squared instead of just x squared, we would have to divide out the whole equation by 3, so that this over 3 would cancel out, and then we have these terms also over 3. But we don't have to go through completing the square. It is useful for the deriving of the quadratic formula, and it is useful for vertex form, which I'll be talking about next, but it's not something I'm super good at, so I'm not going to do it here. So let's erase this and talk about vertex form, minimas, and maximas next. Okay, vertex form. What is vertex form? Well, let's look at the graph again. As I mentioned earlier, there's a level of symmetry, right, where it's almost like you can see a line down the middle where they're kind of evenly split, right? In this case, that line is what crosses the origin here, which is awfully convenient. But, see, whoops, I screwed up. X equals 0. You can see this line right here, right? And essentially what the axis of symmetry in vertex form. Vertex form is, in other words, just either the highest or the smallest point in your parabola. So, in this case, because this parabola sort of slopes downwards, touches the origin, and then goes up, our vertex form is what we call a minima, or a minimum point. So essentially, what that means is it goes. Let me rephrase that. What a vertex point or what vertex form essentially tells you is either the lowest or the highest point. In this case, it's the lowest point because as you go down and down and down, this is the absolute lowest point of our parabola, the origin. After that, it will go up. Before that, it also goes up. There is no lower point on this parabola. So that would also make it a minimum value. If we instead had y equals -x squared, where it's now upside down, as we reach the peak, well, I spoiled it. It's the peak. It's the highest point in our parabola. And vertex form can help you find that. So now let's talk about, I guess, the axis of symmetry. The axis of symmetry is sort of, as it implies, or the name implies, it's the line on which your parabola can be reflected, and that's sort of a fancy way to say it. It's basically the line that just splits your parabola down the middle, right? It goes right through the middle to where the left side is symmetrical to the right side. If x were not 0, if it were 1, obviously this is not splitting your parabola down the middle. The left side is clearly not equal to the right side. So finding our axis of symmetry involves using vertex form and then plugging in that number that we get out of vertex form to then get our axis of symmetry. Now, that is a little bit of work. However, there is a much more interesting way to find the axis of symmetry, because as you'll notice on these parabolas, the axis of symmetry is on the minimum or maximum point. So if you can find that minimum or maximum point, you find the axis of symmetry. So how do you find the minimum or maximum point? There's a couple ways you can do it. You can do it the boring algebra way, where you take negative b over 2a. So, you know, you take whatever your coefficient for x is, your b coefficient here, make it negative, divided by 2 times a. This spits out an x value that you can then plug back into your original quadratic to then get a y value. And that can help you find your axis of symmetry, also by extension your minimum maximum value. Or you could do it the more interesting calculus way, where you, I guess is a little above your pay grade if you're watching this video, but the point is you can also do it that way, and I'll show part of that here. So, as I said earlier, quadratics are just functions. They may look like scary equations, but at the end of the day, they are functions. And functions have what's called a derivative. For now, you don't need to know what that means. Just know that a derivative of a quadratic in its most general form, so if we were to take the derivative of this, that's usually represented as f prime of x. So if our original function is f of x, f prime of x indicates we're taking the derivative. So let's take the derivative of this. Derivative is an annoying word to say. Anyway, so you don't need to know how. I'm just going to do it. So we have 2ax plus b. That's the general derivative, because derivatives of constants go to 0. The derivative of something like 3x is just 3, and the derivative of x squared is 2x. So if you have a coefficient in front of x, like 3x squared, it would become 6x, because you multiply them out. So this is our derivative, and what you do with this is you set it equal to 0. So you have 2ax plus b, you set this equal to 0, and whatever x is in this case, x is equal to, let's give some arbitrary number k. If x is equal to k, you then substitute this back into your original quadratic, so now you would have a k squared plus bk plus c, and this spits out some y value. We'll just continue calling it y, and that combination of k, y is your minimum or maximum value. Now, in order to test what this point is, there's the first derivative test, where you plug in some value that is less than k. So you plug in some value less than k, let's call it h. So you plug in some value less than k, h is less than k, and then you plug in some value greater than k, let's call it l. And then we have l is greater than k. Now what does this tell you? Well, if you get that when you plug in the value of h that is less than k and it's negative, that would mean that it is what essentially happens is you have a minimum value or minimum point. Is that right? Am I wrong? Let's think of the intuition for this. Derivatives are instantaneous rates of change. Yeah, so if some value less than k is negative, that means, let's say our k is equal to 0 in this case. Some value less than that is negative 1. Negative 1 is, well, negative, meaning as you get closer to k, your slope gets less and less negative until you hit 0, 0, your absolute minimum point, and also where your axis of symmetry is. And then when you plug in a value greater than k, L, so it's 1, you get out a positive value, which indicates that your slope is going upwards. It's positive, so that's a minimum value. If you plug in a value that's less than less than k, and it's positive, and then you plug in a value greater than k, and it ends up being negative, that means it's a maximum point. Yeah, it means it's a maximum point. That was confusing. That's my bad. It's calculus, and you'll likely learn the vertex form way with negative b over 2a, but I'm kind of tired and I don't exactly want to explain that right now. I'm also not exactly confident that I know how to do it. So, just use the calculus way. I know how to do that one, and it's way cooler. So that's sort of quadratics explained, I know. Bad video. Not a good explanation. Not enough examples. And there's a lot I haven't explained. Like, you know, non-monic quadratics, which are basically just quadratics where your coefficient of x squared is not 1. Relates to completing the square and whatnot. There's other things you can do with quadratics. What was I missing? Right. Invertibility. Sure, let's talk about invertibility. Oh, and injectivity. That's what I want to talk about. Okay, let's talk about invertibility. It doesn't happen. Invertibility is not a thing with quadratics, because essentially, not gonna need this now, but invertibility essentially states that a function can have an inverse if it passes the horizontal line test. So you've probably heard of the vertical line test. You know, draw some vertical lines. If it intersects with the curve more than once, it's not a function. The vertical line tests both tests for injectivity, and I also believe invertibility. Don't quote me on that though, I could be entirely wrong. But what the horizontal line test tells us is whether or not it's injective, or whether or not it's and whether or not it's invertible. So quadratics fail the horizontal line test when we have our domain as just all real numbers. If we were to restrict our domain to just the positive reals, then it would pass the horizontal line test because we're just not looking at the other half. We would just be looking at this, but looking at the whole thing, it doesn't pass. Right? It intersects with 2 different points here, and that'll happen for, you know, every y value we plug in. No matter how high up we go, we're going to intersect with another part of the curve, meaning it is not invertible. This is sort of an obvious thing, but I don't think a lot of people usually think about it. But what is the inverse of squaring something? It's taking the square root, right? This is what our square root function looks like. I'll get rid of that one too. So, given this square root function, it almost looks like half of the parabola just tipped on its side. So if we do y equals negative square root of x, yeah, it's a parabola. However, the problem with this is it requires 2 functions to make up the original parabola. It's not a function if we just had this whole thing as a 1 function, because, well, square roots aren't defined under real numbers for negative values, so you flat out cannot output a negative value like that, which is why this is not invertible. but that's not something you need to know, just for future reference. Injectivity is something you do need to know, though. Injectivity is just a fancy word for one-to-one. Basically, this function is not one-to-one because you can plug in -1 and get the same value as if you were to plug in 1, because they both hit 1, right? It's a little off there, but -1, 1, 1, 1, right? You get two x values that go to the same y value, which makes it not one-to-one, and by extension, not injective. Surjectivity, or being a surjective function, requires that for every y, there exists at least one x that goes to it, that pairs to it. In this case, parabolas are also not surjective because, as you can see, it's not defined for negative y values here. So it doesn't go to every y, only positive y values in this case, so it is also not surjective. So, you know, it's not surjective, and obviously not bijective since bijectivity is the combination of both injectivity and surjectivity. If it fails one, it automatically is not bijective. So, some fancy words I threw at you there, but essentially, parabolas are not one-to-one, and they are not defined for every y value. That's all you need to know. I think that's it. This video is long and bad. That's my fault. Basically, what you're going to need to know is factoring in the quadratic formula. Maybe completing the square, and and minimum maximum points. You can use the calculus way or the boring vertex way of -b/2a, and you just plug in your values to find the axis of symmetry. But the point is, those are relatively simple, and you can learn that pretty quickly. Yeah, that's my quadratics half explained. I hope I did a half decent job at least, and thank you for watching.